Hello, my name is Shay Moran, and I will present a joint work with Chaim Kaplan, Ishai Mansour, Uri Shtemer, and Nitzan Tur about differentially private linear algebra. Okay, so this project is part of a larger body of work about privacy-preserving algorithms. And just so we have some idea what we're talking about, let's ask ourselves when is it relevant and demonstrate it via the following imaginary example, which I like to call the deep neural doctor. So imagine that you go to your family doctor, and your family doctor tells you about this very huge international project of training GPT, like a kind of a language model, whose goal is to later diagnose people in countries and places where maybe they don't have the best medical care. And the key here is that in order to train this neural doctor, this GPT doctor, they need a lot of medical data, and your medical doctor asks you to share your data with this project. And of course, on the one hand, I think each of us would like to contribute to such a project, to such an effort, but we might also be afraid that this could cause sharing our data, sharing our private and sensitive data. We can be afraid that maybe someone will chat with this neural doctor and will find out personal stuff about us that we prefer not to share with others. Okay, so this example we will remember it and use it again later when we formally define differential privacy. But as I said, it's an imaginary example, but in practice, we know that algorithms, especially machine learning algorithms, they increasingly use and rely on personal and sensitive data, and this happens in a variety of contexts, ranging from social networks like Twitter, Facebook, the way your feed is being managed, recommendation systems, navigation apps. All of these applications, they use, rely, and exploit our data, and parts of it can be indeed sensitive. So the questions that are guiding our research is which tasks can be performed while protecting private data, and more quantitatively, what is the cost of privacy? How much more resources must we use or must we spend in order to maintain, to protect privacy? In this paper, we focus on linear algebraic tasks, and in the rest of this talk, I'm going to first present to you our main results, and then if we have time left, I will also discuss some technical highlights of the paper. Okay, so let's begin with recalling the definition of differential privacy, which is the mathematical definition we use to describe or to characterize when is an algorithm considered to be responsible in the context of handling private data. And as indicated by this slide, this concept of differential privacy is by now a very well-known concept, which is in some sense the gold standard of private algorithms. It is used by Google, by Apple. It is acknowledged by law, by the European law, by the American law. It was used in the American census. It is used by Microsoft, by Uber, and by many other companies. So it is sort of a well-established definition of privacy in the algorithmic context. Okay, so in order to define differential privacy, I will use the example we discussed earlier of the differentially private neural doctor. So remember that the story there was that you go to your family doctor and your family doctor asks you to share your data in order to support this magnificent project of training a GPT, a huge language model that is going to diagnose and cure people all around the world. And you really, really want to help, but you're in a dilemma because you're also afraid that, you know, sharing your data might later cause some bad events. So, for example, someone will chat, some adversary will chat with this GPT, with this neural doctor, and will somehow extract from this neural doctor sensitive information about you. So, you know, there is some event which we denote by E in this slide, which is something you're very, very much worried about. Now, if the deep neural doctor is differentially private, namely it satisfies the mathematical definition of differential privacy, then your family doctor can pacify you by saying that, you know, whatever event you are afraid of, its likelihood is not affected by your decision to participate, to contribute your data. What do we mean by that? We mean that if you consider two parallel scenarios, in one scenario you contribute your data, and in the other scenarios you don't contribute your data, but everything else, except the fact whether you contribute your data or not, is the same in both scenarios. So anybody else who contributed their data contributes their data in both scenarios. The only difference between the two scenarios is whether you contributed your data. And then the mathematical definition says that the probability of every future event that depends on the output of the algorithm is roughly the same in the two scenarios. So a bit more formally, we use the following notation. So epsilon delta, think about them as small numbers, the privacy parameters. So we're going to use the following technical notation. So two real numbers, x and y, are said to be epsilon delta equivalent if x is at most e to the epsilon times y plus delta, and vice versa, y is at most e to the epsilon times x plus delta. And if we remember that e to the epsilon is roughly 1 plus epsilon, then we see that x and y are almost the same. And by almost, we mean up to a multiplicative factor of 1 plus epsilon and an additive factor of delta. And building on this relation, we say that two distributions, P and Q, are epsilon delta indistinguishable if for every event E, the probability over the event under one distribution and the probability of the event under the other distribution, these two real numbers, these two positive non-negative numbers, are epsilon delta equivalent. Okay, so that's sort of the technical definition that is used in privacy. And then, when is an algorithm considered differentially private? So we consider algorithms whose input is a sequence, is an array of data points, Z1 up to Zm. So Zi in the context of the deep neural doctor can be the medical data of the ith patient that contributed their data. And the output of the algorithm is, is whatever it outputs. So again, in the deep neural doctor, it's going to be this huge language model, this huge GPT-like model. And as we will see, the definition of differential privacy really makes sense when the algorithm is randomized. So we really think about the output of the algorithm as a distribution over outputs, right? So for every fixed input, the algorithm defines a distribution over outputs, and this distribution is specified, or the actual output is specified once the random bits of the algorithm are instantiated. So A of S here is a distribution over solutions, over outputs. Okay, and then we say that an algorithm A is epsilon delta differentially private if for every, and this universal quantifier is important, for every pair of neighboring inputs S and S prime, right? So we have two inputs of length M, and they only disagree on a single position, on a single data point, which we call Zi, right? So if you only make one change to the data set, you only change one data point, you only change the medical data of a single patient, then the two distributions over outputs are indistinguishable in this sense that we defined earlier, according to epsilon and delta. So, right, so again, let's go back to the deep neural doctor example. So if you take the bad event E to be all those bad GPTs that later someone is going to chat with them and going to extract some personal data, sensitive data about me. So the probability of this event, that A of S, the GPT that is actually outputted when I give my data, is in the set of bad GPTs that are going to also give away my data. So the set of these bad GPTs, this event, has the same probability whether I give my data or not, and by the same probability I really mean up to epsilon delta indistinguishability. Okay, great. So this is the definition of differential privacy. Yeah, so another technical remark. So epsilon, we will usually think about epsilon as a constant, as a small constant, like 0.1. However, delta, we will require delta to be negligible. So it should be much smaller than 1 over m, where m is the number of data points that the algorithm is trained on. Okay. Now in this paper, we really focused on linear algebra, on differentially private linear algebra. So this is in fact a subset of a broader context of, constraint satisfaction problems. So in a constraint satisfaction problem, we're given a sequence of constraints, and we want to find a solution that satisfies all of them. And in this work, we focus on linear algebraic constraints, like linear equalities or linear inequalities. And we think about each constraint as private, as something that has to do with some sensitive data. So each constraint, right? So our algorithm gets a sequence of constraints, Z1 up to Zm, and each constraint Zi is private. Later, when we will discuss applications, I will point out some examples where this Zi might actually where we get such linear algebraic constraints from natural sort of algorithmic tasks. Okay. So we understand the problem. We want to design algorithms that solve linear algebraic constraint satisfaction problems, like solving linear equations or linear inequalities, linear programming. But let's try to understand what does it mean or how to even define this. So here is the first attempt to define what does it mean to solve a linear algebraic task like that in a differentially private way, right? So we get our sequence of equalities. We have here m equalities, and our goal is to compute a solution that satisfies all of them, right? So we want to find the solution x that satisfies all of these m equalities. And we want that this mapping that takes, the m constraints and outputs a solution, we want this mapping to be differentially private. Now, is this even possible? So, as you might see, this is not possible to satisfy, because the mere existence of a solution is unstable, right? So imagine we would have such an algorithm that in a differentially private manner outputs a solution when the system is satisfiable, and imagine that the system here on the right is satisfiable, right? So with probability, let's say 0.9, it outputs a solution when it gets as input the linear system on the right. But then, we can take the ith equation and replace it by whatever 0 times x1 equals 1, by something which is clearly unsatisfiable. And then by privacy, whatever solution we outputted on the right system, we should also output on the left system, right? So if on the right system we output a solution of the right system probability 2/3 or 0.9, whatever I said, so also on the left system we should output a solution that satisfies the right system with probability maybe now 0.8. But this is clearly a wrong solution to the left system, because the left system is unsatisfiable, right? So this really shows us that it is impossible to solve a system of linear equations in the classical sense, just because the mere existence of solution is unstable. It's unstable with respect to changing one equation in the system. Okay, so what to do? So I think a natural compromise, and this is also the compromise that we make in this work, is to output a solution x which satisfies many equations. So it does not have to satisfy all equations, but it should satisfy many equations. And by many, we really mean as many as possible. And as you will later see, how many is actually possible is an open question, which I think is very interesting to explore. But for now, just think about many as, like 0.999 of the equations in your system. That's what we want to get. Okay, so we are now ready to present our main results. So we start with our main result in a system of linear equations. So our algorithm here does more than just solving the system in a differentially private way. What it does, it actually generates a synthetic linear system in a differentially private way, such that the synthetic system and the original system have approximately the same solution space. Now, this is stronger than simply solving the original system, the input system, in a differentially private manner, because once we publish this synthetic system, we can later apply any classical algorithm on the synthetic system and just use the solution we computed. And the composition of the two algorithms, the synthetic system generator composed post-processed by the classical linear system solver will also be differentially private, and this is a basic property of differential privacy called post-processing. In more detail, our algorithm outputs this output system, and it satisfies the following. So every solution to the input system is also a solution of the output system, right? So we don't lose any solutions. We might add some solutions, but still every solution that we add solves almost all of the input equations, and almost all means almost all except an additive factor of dimension squared divided by epsilon. And I want to stress here that the dimension here is the actual dimension which is of the span of the rows of the linear system. So it could be that the linear systems have many parameters, but the actual dimension is very low, and our algorithm really depends on this lower dimension. And as I said, with this synthetic system generator, you can later solve the synthetic system in a classical way, and the overall algorithm will be differentially private. And quite surprisingly, there is not much of previous work on this basic linear algebraic task. So previous work only considered the real field. So our algorithm applies to any field. Previous work only considered the real field of the real numbers, and they mostly work on subspace approximation. Namely, you have data which is very high dimensional, but maybe it lies on an affine subspace of much lower dimension, and the goal is to approximate this subspace in a differentially private way. And yeah, but most previous work really assumed that the data is nice and well behaved, and as I said, our result is general and arbitrary. And there are also nice applications of our linear system solvers. So one is that it implies almost immediately a learning algorithm for subspaces, right? So imagine that you want to learn in the back sense, in a probably approximately correct sense, subspace of dimension d over some vector space, and it's also a key subroutine in the linear programming differentially private solver, which I will present later. And as I promised, one open question here is: what is the minimal number of unsatisfied equations in this task, right? So let's say we want an epsilon delta dp solver for linear systems. What is the minimum number of equations that we can guarantee that are not satisfied by the solution? So our result gives something like dimension squared divided by epsilon, and the conjecture, which is also a lower bound, is dimension divided by epsilon. Okay, so now we will move to discuss our second main result, which is a differentially private linear program solver. So the input of this algorithm is a sequence of linear inequalities over the real numbers, and we will assume that the system is satisfiable, and our algorithm outputs a solution X, which is guaranteed to satisfy all except maybe an additive factor of which is polynomial in the dimension, in the privacy parameters, and in the bit complexity of the input numbers. Okay, now on this problem, on differentially private linear programming, there is more previous work. So, and in particular, our algorithm heavily relies on this previous algorithm by Dunagan and Vempal from 2004. Now, in this paper, they did not consider differential privacy. However, their algorithm does imply a differentially private algorithm, which is valid as long as the linear inequalities are define a full-dimensional polytope or polyhedra. We need to work quite hard in order to handle lower dimensional systems, and in particular we need to use the previous result about linear equalities. Other previous work gave inefficient algorithms, so they missed much less equation, much less inequalities. So here we have only 2 to the log star b rather than b, but the algorithm is inefficient. It's not polynomial in the dimension. And there are also works that provided weaker approximation guarantees. So, for example, there are works that only approximately provided solutions that only approximately satisfied most of the constraints. In terms of applications, we use our LP private solver in order to give the first polynomial time algorithm that PAC learns half spaces under differential privacy in the realizable setting, and also another very important problem, which we call differentially private convex combinations, or differentially private interior point problem, and we will discuss this problem next. Now, in terms of open questions, I think there is one obvious and interesting open question, which is to characterize the minimal number of unsatisfied constraints, of unsatisfied inequalities. Our result gives an additive factor of which is polynomial in the dimension, the bit complexity, and the privacy parameters. We know that that are inefficient algorithms that only miss log star in the bit complexity, and maybe that's also a conjecture which is interesting to explore. Can we guarantee that the number of unsatisfied inequalities only depends on log star of the bit complexity rather than the bit complexity itself? Okay, so we are done with discussing and presenting the main results. Now, in the 10 minutes I have left, I want to mention 2 highlights about what I call the curious landscape of differentially private linear algebra, which I think is interesting. Okay, so the first highlight concerns duality. So let me first explain what I mean by that. So there are 2 natural ways to represent polytopes in RD. One way is just, I give you the names of all of the vertices, and you have all convex combinations of the vertices, right? So this is one description of the polytope as a list of vertices. Another sort of dual representation is by intersection of half spaces, right? So I give you a sequence of linear inequalities, and you look at all solutions of this system, and these two descriptions are sort of dual to each other, because one uses vertices, whereas the other one uses the faces of the polytope, hyperplanes. Similarly, we have the same phenomenon when we describe affine subspaces of RD. So one way is to just give you a basis to the affine subspace, and you just consider all affine combinations of the basis, right? So remember that affine combinations are linear combinations where the sum of coefficients is 1. A dual description uses linear equalities, right? So I give you a linear system and you look at the solution space to this system. This will again be an affine subspace of the vector space. Now we can also ask the feasibility problem with respect to both of these formulations, right? So linear programming, we consider the dual formulation of the dual descriptions of polytopes or polyhedras, right? So we have a polyhedra which is represented by a system of linear inequalities, and we need to output a solution to this system, namely a point in the polyhedra. Similarly, the linear equation, linear systems are a feasibility problem with respect to the dual formulation of affine subspaces. We could also ask the feasibility problem for the other formulation, but we see that it becomes sort of trivial, at least if we think about, if we don't consider privacy as a constraint, right? If I give you a polyhedra represented by its vertices and you want to output a point in the polyhedra, just output the first vertex, just output one of the points in your input. Similarly, if I give you a subspace, an affine subspace, which is represented by a basis, and you will need to output a point in this subspace, you just output the first point in the basis. So while on the left-hand side, the formulation of the feasibility problem or the search problem is kind of a fundamental linear algebraic task that is very well studied, on the right side we have trivial problems that haven't been studied, at least not classically, for a good reason. But it turns out that once you add privacy constraints, then also on the right-hand side, the problems that we get are highly non-trivial. And indeed, if you want to maintain privacy, you cannot just output a point from your input, because it will compromise the privacy of this data point. And in fact, it even this problem of convex combinations, right? So outputting a convex combination of a list of input points is a fundamental. It is becoming clear that this problem is a fundamental geometric problem in differential private algorithm design. So there is a list of references here that use this problem as a mean towards solving other problems, like learning half spaces or outputting medians and all sort of things, natural things like that. And this problem has also been studied in its own right. And in fact, what we show in our paper is that the primal and dual formulations are in fact equivalent to each other from a differentially private complexity theoretic perspective. So we give efficient private reductions from the two sides to one another. I will not have time to describe how we do it here, but let me just note that the equivalence between linear programming and convex combinations is done by an ellipsoid perspective, like something similar to the ellipsoid method. And the equivalence between solving linear systems and outputting affine combinations is done by a very elegant combinatorial process of peeling bases, a process which in fact applies or is well defined for arbitrary metroids. And it's very simple, but the analysis is somewhat interesting. Okay, the last thing I want to discuss, and this will be quick, is weak versus strong polynomial time computation. So, classical result is that linear programming LP can be solved by a polynomial time algorithm. This is a classical result from around 50 years ago. But all efficient algorithms for linear programming are only weakly polynomial time. So what does this mean? It means that the runtime scales with the bit length of the inputs. And it's and this is in contrast with strong polynomial time solvers, in which the number of arithmetic operations is just polynomial in the dimension and the number of constraints. And a major open problem in the area is, are there strong polynomial time LP solvers? And this is also related to Hirsch conjecture in geometry. Now, a nice observation is that in the context of differentially private algorithms, this conjecture is resolved. What do I mean by that? So our paper implies that there exist weak polynomial LP solvers. That's what we do. And on the other hand, strong polynomial time private LP solvers don't exist, and they don't even exist in 1D, and they don't exist for an information theoretical reason rather than a computational reason. So I do not have time to explain this, but it really follows by combining previous results, specifically a result by Bani, Sim, Stemmer, and Vadan, which implies that that even in 1D, if you want to find an interior point, your running time of your differential private algorithms must scale with the bit complexity of the input. Okay, that's it. I thank you for your attention. You cannot ask me questions in this video, but I welcome you to ask us questions in the conference or by email. Thanks a lot. Bye-bye.